Yes, both speakers are listed on the site.
Yeah. But what's I'm just trying to see if I have a phone number for Manas so that I can call him. No, I don't think I would call him on phone, so it's all email.
Okay.
Well, let's see. I think one of the things we can do is that if I guess Manas was supposed to go first and then Louis, but we can start with Louis in the interest of time.
Okay. How long do I have?
Supposed to be half an hour each. So
Okay, half an hour. Okay.
Okay,
So-
so I will formally start the meeting. Welcome everyone to the Ontology Summit 2026. Today is the 25th of March, 2026. And we are continuing the Ontologies and AI track today. And our co-hosts will be Gary Burcross and Ram Sura. So I will turn it over to them. Go ahead.
So, Gary, you want to take over or?
No, Ram, why don't you, since you invited
Okay.
Louis?
Yeah. Anyway, thanks everyone for joining. Today we have two very interesting talks on neurosymbolic AI. We're still waiting for the other speaker to join us, but we'd like to thank the speakers. Our first speaker is Louis Lamb, and as you know, Louis has been pretty active in this field of neurosymbolic AI. And in fact, one of the papers that he wrote in the Artificial Intelligence Review about a couple of years ago has almost 1,000 citations on this area. He has a lot of good insights into it. And then will let Louis talk right now. I believe Louis with Catholic University.
Yes, yes.
And I will let Louis start his presentation.
Thank you so much for the invitation. It's an honor to be here, and I'll try to bring a glimpse of the field for those who might not be very familiar with the areas, and I'll try to be comprehensive. I know it's hard to be in half an hour, and I'm trying to bring as well some insights from what's happening in industry with respect to neurosymbolic AI, and how we can see that the field is becoming more and more attractive, and in a way is gathering more attention from different areas or sub areas of AI and computer science. So in the talk, I give some basic concepts, introduction, evolution of the field, how integration of learning and reasoning is coming to the fore, is getting more and more attention, especially because we have very successful applications of machine learning, but however, we see a lot of limits in terms of the reasoning capabilities of the tools that have become very popular these days, not only in industry, but across the spectrum in other fields. What kind of approaches for neurosymbolic AI we have, and what is conceptualization of neurosymbolic AI? And some perspectives that I hope we can discuss in a more informal approach as well. So if you want to read or have an idea of the field, I think Ran mentioned about this paper, the second paper that we wrote some years ago, and still very up to date in terms of the trends and how the field is being organized over the last years or the last decade. And also there is an interesting paper as well that looks at some formal aspects, this mathematical framework and learning techniques for neurosymbolic systems, that I think it's an interesting paper that's also being posted on arXiv as well. So the big question in AI has always been the first one, I believe, at least for some of us. We have been investigating if digital machines can think. This is not a novel question, right? Even before electronics, Pascal, Leibniz, and other researchers and mathematicians, engineers, they have been asking if we could build artifacts that would mimic the way that we reason, or they show some cognition. And this was a big question around the times of Turing, and then in the late 50s when AI came to the fore after the famous Dartmouth meeting organized by McCarthy, Minsky, Shannon, and other luminaries of the field. And coming to a big jump to today, where we are using these large language models, Gen AI. So one of the questions I did a few weeks ago were, okay, are you neurosymbolic? And I asked them if they were, and these are the answers they provide. Gemini is not a purely neurosymbolic AI system in terms of architecture. You can ask the question yourselves. You might get a different answer. But these systems that we've been using these days, Claude, I also asked Claude and other AI models, language models, if they are aware or if they are neurosymbolic. And the answer I got today, this morning, just before the talk, about an hour ago, I was saying, okay, let me ask Claude again if Claude is neurosymbolic or not. And the way that Claude sees itself, it's not neurosymbolic AI in the technical sense, but it gives a long explanation about why it behaves as if Claude was reasoning or proposing a way of reasoning versus pattern matching in the way. So at least I think they have been programmed to respond that they are not purely, or they're not effective neurosymbolic systems in the way that we see systems where reasoning and learning have a semantic component that's crucial in the sense of building sound AI systems. So we are not there yet. So we have to go back and keep doing our research, the hard work in terms of research. Okay, let me pause a little bit and mention that this integration between learning and reasoning is not only a subject that has received attention recently, but in history, yet already in the 1940s, when McCulloch and Pitts proposed their first artificial neural network model, soon after that, researchers like Stephen Klein is well known for his studies in regular language, in finite automata, and other results in recursion and computability theory. One of the key motivations for Klein to study finite automata was to analyze what kind of events neural networks of McCulloch and Pitts were processing or computing or identifying or recognizing. And so one of the key papers that Klein published, and even McCarthy at the time, was to analyze, what kind of reasoning, what kind of meaning the proposed neural nets that they had at the time were capable of represent, compute, or learn. So this question is actually not new. This question is a question that has been around in science with other disguises, with other, let's say, presentations and other abstractions. But coming to more modern times, the reality is that we're living a time where technology has, dominated our lives in terms of not only the impact that we have in our research world, in our academic life, or in our professional life as computer scientists or engineers, but AI and computer science have been even recognized as very valuable fields of scientific discovery, even more so. And it's a very strong recognition that we received in terms of the Nobel Prize in 2024. Both the Nobel Prize for Physics and the Nobel Prize for Chemistry recognized artificial intelligence AI research and the results that we are bringing and the paradigm shifts that we are bringing to, let's say, to the hard sciences, to the sciences that historically have been considered, let's say, the prominent sciences that we have in the world: physics, chemistry, medicine, biology, and so on. So AI has now an impact that goes well beyond our small community that we had, let's say, up to 20 years ago, when AI or machine learning and the related fields were considered like niche fields, even from a computer science perspective. If those who have been around here for more than 20 years will remember that even the subfield of AI was, let's say, one of the smallest, or not one of the smallest, but a smaller division within computer science. But the reality is that AI has had a huge impact, And the impact is being compared to the impact that the web had from the 90s when we started using networked computers via the internet, using the web technologies that provided us with a much easier interface with much easier communication mechanism to communicate between humans and communicate between people in companies, people in education institutions, and so on. Right. So I'm trying to move into neurosymbolic AI. And another motivation for neurosymbolic AI is that the current technologies, as powerful as they are, they have limits. And from time to time, we see some news in the media, in specialized media, saying that some people get surprised by some of the limits that, say, the purely neural approach or purely machine learning approach of AI has. And in particular, this news here, it caught my attention because a well-known phenomenon when you work in automated reasoning, theory improving formal systems, is that dealing with negation is something hard to deal with. Those who have ever tried programming in Prolog know that dealing with negation requires some special.
Louis, can I have a minute of it? I think
yes, sure.
You should put your stuff in the presentation mode. That's one of the comments.
Am I not in the presentation mode?
No, you're not in the presentation mode, I think.
Oh my God.
Yeah.
I see the presentation model here. Okay.
Maybe
we see your speaker notes. We see your speaker notes.
Oh, no problem. Oh, you are seeing the speaker notes because we are in between friends. There's no problem that we're seeing the speaker notes. But I'm going to try to increase the size here. Just a second.
I think maybe you are using two displays.
Oh yeah, maybe I'm using two displays.
Two displays, then you have to switch the display. Otherwise, see, it's showing.
Oh, that's a pity.
Showing the presentation mode.
Yeah. I always use two displays.
Yeah,
old habits of a former computer programmer. Okay. Just a second here. That's a pity. Desktop one. What can you see now?
Go to the presentation mode.
No,
it's still the same thing. And the reason is that swap displays. Look at the slab. Okay. Go to the presentation mode.
Yeah.
And then then you'll see a swap displays. Do that.
Oh, yeah. Just a second. Presentation mode, swap displays. Can you see it now?
You're okay now, yeah.
Oh, okay. Oh, sorry about that. I apologize. I thought it was okay. Okay. So one of the things we have to pay attention to is that now it's okay, right? I hope it's so. Okay. Oh, sorry about that. I apologize. So one of the things we see is that there are limitations, and especially when you see the news, some surprises like, some Gen AI tool not being capable of dealing with negation. And then people start to realize, oh, well, why can't these tools deal with negation? And then people start to go back and then they say, oh, people who work in symbolic AI, they've been facing this problem with negation for 40 years in automated theory improving, in programming languages, and in logic programming and so on. And so people realize the reason that, we need other tools other than only focusing on deep learning based approaches, right? So, and this kind of thing bring to the fore the need for us to be a little bit more careful in the ways that we develop current AI systems, to have systems that are more reliable and actually are more trustworthy in sense of applications. If we think here in terms of medicine, and here is, it's clearly a medical image analysis based on a visual language model or on a visual model that's not capable of providing the right diagnosis if, the doctor or the user starts interacting with this tool and provides some sentences and some questions that contain negation, which is very common in human discourse, right? And the point here is that neurosymbolic AI then offers this solution for some or for a large class of these problems, because we can bring techniques that have been developed for many years in computer science that deal with automated reasoning, deal with formal reasoning, and then we can learn how to reason formally about these very powerful tools that we have and that are based on the transformer model or based on neural networks. And that's the whole point of the research that we have been doing. We need self-explained architectures. We need systems that are interpretable by constructions or systems that are at least explainable, that you can explain their behavior. That's where neurosymbolic AI can provide an interesting contribution. So just to give you another following up where the area comes from. And just to remind that in the early 2000s, even neural networks were not that popular in the AI community or in the computer science community. Even at the New Reaps conference early in the early 2000s, neural network papers, there were, let's say, a minority section if you compared with, kernel methods, with SVMs, Bayesian learning at the time. And we had some very interesting results provided by Jeff Hinton and some people that work in this community that prove that deep belief nets and deep neural networks with several layers of neural networks could provide and could enhance the performance of computer vision, pattern recognition algorithms, pattern recognition systems, and so on. And this is the history of how deep learning became very popular, right? And today we got to the point where we had these very powerful language models, but another point that people make is that it's becoming more and more expensive. The energy footprint, CO2 footprint, and the use of energy, the energy requirements, and the cost of training and maintaining these models is becoming really exponentially higher. As you see here, from the beginning of the very large language models that we had about 6, 7, 8 years ago to today, the cost of only training these models is in the hundreds of millions of dollars. So this is becoming very expensive, and maintaining and operating them at inference time, at running time, at the deployment time, as we do in industry, is getting very, very expensive. And even the companies that are developing them, they are still in the investment phase. They're still gathering more and more capital to invest in these models, but they are not seeing the profits at the moment, right? So there are needs for not only from a cost perspective, from an energy perspective, but also there are other issues associated with security, safety, reliability of the models. This is a report. This was published in the AI Index report, and companies that have been using novel and modern AI technologies, they face several challenges with respect to safety, to security, to kinds of incidents that organizations face when they deploy AI in an industrial setting. So there are several aspects that around modern AI that motivate the use of more formal techniques, of techniques that use automated reasoning approach, the techniques that strongly integrate learning and reasoning, integrate neural networks and logical reasoning, or that use theorem provers, hybridized with other language models like Amazon is doing, like other companies are doing, and that I hope I can illustrate some examples coming forward in the presentation. So in the end, the point that I wanna make here is the point that we have to know why technologies work. And technology becomes successful when scientists can explain why do they work. The recent Nobel Prize for Economic Sciences, the latest one in 2025, was given exactly to researchers that investigated why some technologies become influential in the economy. And some of the conclusions that they got is that the economy accepts, or the economy absorbs technologies and goes into a transition phase where these technologies become very useful when we are capable of explaining them and make an economic sense, not only an economic sense of the technologies, but also we can explain why scientifically they are robust and why we can use them over time. Right? So the Industrial Revolution happened after we could explain how electricity worked, how the engines work, how we could distribute energy, because we had a complete control of the scientific underpinnings of electricity and magnetism that led to the scientific revolution. And that's the expectation that we have about AI. From a more technical perspective, how we integrate learning and reasoning. Recently, also, people have been drawing analogies between this dual process theory of Daniel Kahneman that, popularly, I'm overly simplifying here, organizes the way that we think in terms of cognitive processes into systems. One system is a very fast system that recognizes patterns that we've seen before, that we immediately react when we are in danger, or we automatically do tasks that we've been training our whole lives, like crossing the street, for instance, or driving a car, things that we do automatically after a long period of training. And whereas system 2 is more reflexive, when we are confronted with new situations, we have to stop and reflect. When you are learning a new language, when we are trying to prove a new result, when we are conducting a new experiment in a lab, or when we are doing scientific research, we stop and we think and reflect. It's a much more reflexive system. So this system 2, system 1 have been, drawn a parallel or an analogy between Kahneman's system 1, 2 dual process theory and the theory of neurosymbolic AI systems. And this also brings some analogies with the schools of AI over the years that we had in terms of symbolic AI, here represented by Alan Yu and Herbert Simon. As you know, some of the pioneers of AI, they invested in theory improvers, in symbolic systems. Later, we had the school based on neural network theory and on neural learning. But we also had people who operated in between. We can say that Les Valiant, in his work on pack learning, on his work on integrated learning and reasoning, always saw the value of integrative approaches. The same way Judy Pearl, in his work on causality, he also saw the need to integrate symbolic techniques, Bayesian techniques, with machine learning to have systems that were more robust. Right? And in our approach goes in a way that we want to develop tightly knit systems where the neural network itself will be both the learning engine and the reasoning engine. And in order to do so, what we did was to investigate what kind of logics neural network models could process, neural network models could learn. Another requirement that we saw in our research that we identified is that we don't need only to represent information that is static, information that is represented by propositional logics or by first order logic or by predicate logics. We saw a need in computer science, in AI, of representing a temporal dimension, in represent a knowledge dimension, in represent several different modalities. And that suggested to us to use or to identify ways of representing modalities of reasoning in neural networks, or at least to investigate what kind of model logics, what kind of model reasons we should be able to represent in a neural network to have richer system, a system that not only represented classical logic that has its own limitations, that has been designed with a very specific purpose, but other computational logics that have been designed more aligned with the needs of computer science. So this was the motivation of our initial work. So the idea here, for instance, if we think in terms of neural networks, was to identify if neural networks could be the proper framework to represent, or how to identify in what ways artificial neural networks could represent, for instance, the knowledge expressed by model logics, right? The relations between agents that interact in distributed systems, how we could represent the knowledge of those agents. And what we are capable of doing at the time was exactly to show that there are ways of constructing neural networks where you can have fragments of model logics, or even fragments of what we call, and which is technically called model logic programming, which is an extension of logic programming with model operators. And in this way, you can represent the knowledge of agents. We can even represent the interaction of agents and agent exchanging knowledge using communication mechanisms that we can design using neural networks or neurosymbolic agents as an architecture to represent each individual agent that interacts. In that way, we are capable of representing, and we are capable of showing that neural networks can indeed solve certain test beds or certain benchmarks for multi-agent interaction. If you remember the book by Ron Fagan and Joe Halpern, the late Joe Halpern, Moshe Vard, and Yoram Moses, they wrote this great book on reasoning about knowledge, is a book where they explain how multiple agents or multi-agent systems exchange information and reach common knowledge about solving certain problems. What we tried to do in our research was exactly to see if this approach that they developed could be extended to a neuro-symbolic framework where the agents not only are capable of doing deductions and reaching common knowledge or common agreements about the solution of a problem. And if you think in terms of the Muddy Children puzzle or other puzzles that are typical of the multi-agent systems literature, we're capable of showing that not only a neural network-based engine could solve the reasoning problem, but could also learn and improve its performance over time. Right? So our approach was based in this principle. Let's not only bring the classical results or the results from classical logics and from predicate logics into a learning perspective by designing neural networks or algorithms that can learn, let's say, first-order logic or fragments of first-order logic. We are aware of the undecidability results that we have around that. That's why we work with fragments of logics. But also we are trying and we organized a way of, or we developed a way of learning different model logics or different logics that could deal with the knowledge of agents, with the uncertainty of agents, and with the knowledge of agents that evolves in time, right? So this was the key motivation for our work. And from an industrial perspective, from an application perspective, about a decade ago, one of our students did his PhD thesis on a work that was very pioneering for the time. I think it was way too ahead of time. I think he was one of the first researchers who were capable of integrating a learning engine with a model checker, right? So in that way, what the student did at the time in his thesis and later in the publications around 2010, 2011, or 2010, 2012, was to show that he could use, right, a learning engine to use the counterexamples provided by a model checker to refine the specifications of the model. In that way, we would have an adaptation engine that could improve the model specifications or the system specifications of a system and of a given software system or a given hybrid system or a given complex system. And we could use learning to automatically improve the specification, reducing the manual labor that we have when we are specifying properties of a system or when we are defining a model of a system. And to my surprise, I've been reading several papers in software engineering that are now adopting exactly this principle. They use counterexamples from a model checker or from a verifier or from a certain tool. And this counterexamples is now used as input into a language model or into another learning engine exactly to refine the model specifications. So already about 10, 15 years ago, we showed that this was a possibility in terms of a potential to have neurosymbolic AI contributing to crucial applications in software development, in software verification, and in program verification. Another important application that we see in industry today of neurosymbolic AI is the work that Amazon and other companies are doing. They are using they call their approach neurosymbolic, but what the Amazon is using is that on top of their language models or on top of their Gen AI applications or their heavily intensive machine learning systems that they have with the data, you can imagine that the quantity of data that Amazon has, they use a theory improver to guarantee that the outputs of the systems will behave with respect to the specifications at runtime. And this is very important because one can imagine that Amazon and some of the very large companies, they are, for instance, analyzing credit scores, they are analyzing behavior of customers, they are analyzing fraud at runtime, and they have to provide guarantees that their systems will behave and will be solid or will be trustful, from the perspective of not only the company, but also from the perspective of those who are using the systems. And they have to provide guarantees that the system will operate at runtime with the same guarantees and the same stability and the same precision that purely symbolic systems work. So now neurosymbolic AI is getting also attention with respect to companies that have noticed that there are the need to guarantee that the behavior of this huge AI system that we use today are providing the answers that we want with the level of precision of the accuracy that are needed in terms of deployment time, in terms of inference time, right? So finally, another example that I want to bring here to the fore where neurosymbolic AI is also gaining attention is that according to certain mathematicians, and Terence Tao, who is very well known from UCLA, Kevin Buzzard, and other mathematicians, they are seeing a lot of value in AI techniques to help them improving and in advancing mathematics research. And one of the systems that can be used by let's say in general, is those systems that the Google DeepMind has developed, for instance, alpha geometry. And it's also a hybrid system where on top or aligned with or combined with the language model or the system that's based on neural networks, we have also a symbolic system that uses hypotheses that are created or generated by the neural network-based engine. And these hypotheses are used as lemmas to construct new results and to prove new results about certain domains. So here there also has been identified a way where neurosymbolic techniques not only can provide insights to research, but can also, to research and to also to commercial applications, as I mentioned before, but can also provide insights and tools to advance mathematical research, to advance scientific research. And as you know, scientific research is even more rigorous than certain or than I would say than any other, so let's say, domain of human life, because we are always testing hypotheses using the scientific method and using rigorous techniques to guarantee that the results that we are producing are reliable. And neurosymbolic AI techniques have been shown to be useful in advancing mathematical research, which is something that we believe is another quite relevant result of recent times. Right. So unfortunately, I do not have enough time to go over all the slides, right? So I prepared the slides for a longer time, but I just want to conclude here saying that in conclusion, neurosymbolic AI represents an opportunity for a paradigm shift in artificial intelligence research, in the sense that now not only you can use powerful deep learning systems or machine learning systems that provide some very interesting results in terms of pattern matching, computer vision, in terms of language, translation, language use, but what they lack is a semantic understanding and a rigorous understanding of how the reasoning process happens, not only in our cognition, but also in the scientific disciplines of logic, computer science, and mathematics. Neurosymbolic AI can be seen as a way of unifying learning and reasoning. We in that way, we provide explanations or interpretations for systems that are built with interpretability by design, or we can use neurosymbolic AI to try and build explanations post hoc. That's not my preferred way of interpreting and understanding systems, post hoc explanations. I would rather build systems by design that are interpretable and therefore explainable as well. And also neurosymbolic AI, given the results that we bring from logical systems, from the computational logic community, it can also be a tool that help us to show properties or verify properties of the systems in a way that we can build more trustworthy AI systems. So that's why we say that neurosymbolic AI, or let's say the third wave of AI, is a way of combining not only the neural network approaches that are dominant today, or neural network-based approaches that are dominant in industry today, but also we can bring, let's say, the full history of computer science results that we have in rigorous logical reasoning, in rigorous computational logic, that can clearly benefit artificial intelligence research, artificial intelligence applications, in the same way that program verification and automated improvement have benefited other fields of computer science and AI. So I apologize for the beginning of the talk where there was a problem with the screen sharing, and also I apologize a little bit because I prepared slides for more than half an hour, but I hope that we can have a conversation after the second talk. Thank you so much for your invite. Thank you.
Thank you very much, Luis. Ken, a quick question. Do we take questions now or later on? Ken.
We should wait until after.
Okay, so let's wait
second
until
talk.
Manas, because one of the questions that may come up, Luis, is that what the role of ontologies in this neurosymbolic
Yes,
integration. So maybe you can answer that question after Manas's talk.
I will. I love ontologies. The one thing I didn't mention here.
Yeah. So anyway, we'll that's a question that you might want to come back. Manas is at University of Maryland, Baltimore County, and he's been working on this for quite some time. He calls it knowledge infused learning. He's also a book coming out, I don't know when, but in the near future in this area. So Manas, go ahead. You have to unmute. Okay.
Okay. Yeah. So I'm sharing my screen now. Okay. Is my screen visible? Uh, uh, okay.
Okay, good.
I hope my screen is
No,
visible.
yeah, you're good.
Okay, sounds good to me. Thank you, Ram, for the invitation. And it's been quite some time after I'm coming back to the forum for presentation. And over the past couple of years, I've been focusing pretty much in the intersection of the generative AI and the neurosymbolic integration, which something is driven by my thought that we are heavily driven by data and relatively less on the knowledge part. So what I've been looking into is how we can actually have a generative AI models driven by the neurosymbolic science. So the focus of the talk today is not going to be very much domain specific, but a bit of the exacting about would be domain specific as well. So the notion that I started with, that we have this huge race of developing data-driven generative AI models, which are getting bigger and bigger. We talk about GPT-5, Claude, and Gemini, and so on and so forth. And we have this de facto strategy of doing fine-tuning of these models for various applications for different tasks. The challenge that we see is that these models are, most of the time, the information that we get are not satisfactory, and we do not have any calculated way of means to figure out how do we nudge them in a better way that they can give us the desired information. So even if we do fine tuning, we end up sort of overfitting these models to the domain and not really get an idea about how they can really work in the more what Louis was talking about, in a more explainable and interpretable manner, right? And the question is that we do not have at this moment, and I'm this is to the best of my knowledge, that we do not have a principled mechanism about what these models know and whether that knowledge remains stable over the time in the distribution shift, in the domain shift, or in the adversarial conditions. Right. So, for example, let's say I have a model that is being available in the mental health space, for instance, which fascinates me a lot. Um, can we have this model working in the cognitive behavioral therapy, right? Can this model do the screening? Can this model be able to do some clinical summarization? So for every different task, we just keep on fine tuning these models for different applications, which make them more data heavy as opposed to knowledge heavy or knowledge driven. That's the major piece, because with the knowledge, you do not really need to memorize things. You do not need to claim things, but rather be more specific in your responses. So what I've figured out that LLMs exhibits the systematic bias towards high frequency designs, and their understanding is pretty much pattern matching as opposed to a genuine understanding over the domain. And I added over there the word genuine clinical understanding, because that's where most of my work in the mental health space is being driven, where I've been looking at how these generative AI models can be brought to, and can we have a feasible solution from these generative AI models in the mental health space, where we are already going away from that point that these models are not able to do a real world deployment, for instance. So this thing is not something that I am the only one who is looking at, but there are some neuroscience researchers who have have taken a deep dive into to understand how these neuron specific feedbacks in LLMs work, and are they connected to the brain? So think of this in a scenario where where neuroscience researchers are trying to understand what is happening inside the LLMs. What are the connections? What are the concepts being represented? Are those concepts related to the task, or they are irrelevant to the task? So so far there is no plausible answer to this question, but this is where I see a huge promise from the neurosymbolic AI community, where we can understand a lot of these informations through structured knowledge graphs or different forms of knowledge that we are having at our disposal. The question is, what are the methods that we can devise to do that precisely? So that's going to be the focus that I want to drive in this talk. Right. So, keeping this fact straight, I'm not a huge proponent of scaling. We really do not want large models to do our task. We really want more interpretable and transparent models. Retrieval augmented generation that came into the picture did not really solve the purpose of black boxness of these models, and then people started uh, looking at probing as one of the cases in the LLMs to figure out what are the different reasons that these models do. For instance, you can think of probing as sort of putting a lens over your LLMs and see what are the connections and what are the causations and correlations happening inside the LLMs. Now, when we look at these designs, right, the problem arises is what I call it as an impossible triangle, and we are getting stuck into that with the current generative AI model strategies. First of all, we are heavily driven by scale. We are losing interpretability. Even if we are going over the interpretability, which the Google DeepMind came up with, called the Neuronpedia, to allow you to look inside the LLMs, we are looking at interpretability, but we do not have a definite way of doing grounding, or we do not have a definite way of um, basing these models over a particular structured knowledge. So things of them, much of this information are probabilistic in specific. Even if we do grounding using retrieval augmented generation, it's not scalable, because retrieval augmented generation, think of this as a traditional IO operation, input output operation, which is taking a lot of time. And no matter what happens, RAG is sort of the slowest piece of design. And if you want to make them fast, um, either you have to sacrifice in your structured data, or you have to sacrifice in your models performances. So there is always a trade-off that we are getting stuck in the RAG scenario as well. So when we talked about this recent interest that rose in the LLM space called the probing, we are trying to understand what these models are actually looking at, right? What are the concepts that it is looking at, and are those concepts important? Are they relevant to the task or not? Right. So we become more towards correlations as opposed to causations, and causations means like, are the two concepts connected just because they are meant to be connected because of the data, or are they connected because there is some sort of an external knowledge that is guiding them, right? And is that knowledge correct? And we can actually cross check them through some kind of a visual means. But when we look at this probing mechanism that have been developed in the recent couple of months, we see that they are very much data driven again. So we need to think of this, that if I want to understand if my model is doing a good job in truthfulness, which is the Google's flagship data set of truthful QA or truthful question answering, I am using another set of data to understand whether the truthfulness is actually truthful or it is a fabricated piece of information. So what we do is we create adversarial data set, right? And we are not testing them against knowledge. We are testing against another set of a data set, which we construct as an adversarial set. Now, now the question arises, how can I know that my adversarial set is complete, is correct, and is plausible for the probing task, right? So there are some lot of these questions that arises in the way we define where we define how do I look inside this network and able to make sense that, oh, these connections are correct, these connections are incorrect, and things of that nature. So this is where I see that neurosymbolic AI fits perfectly to answer the questions that neuroscience researchers have, even the questions that raised by broader AI community per se as well, where we try to examine ways in which we can incorporate domain-specific knowledge, lexical knowledge, common sense, and constraint-based knowledge that exist in various applications to guide the model. Let's say, when I say guide the model, I'm trying to say that I'm not saying to fine tune the model, but here's a base model that pretty much do a good job in generating the text in a manner. I want to steer that model. I want to move that model in the direction of my knowledge. And that's the thing that I would really want to do. And now in that process, I want to also chop off some unnecessary connections. I want to remove some of the layers that are not needed at all. That's a like this work also, this sentence that I just spoke, that we want to cut some of the layers, is nicely explained by Max Tegmark in his recent paper on stitching networks, where he say that we do not really need this big network to solve problems in the real world space. So this is where my intention to do a more knowledge infused design for these generative AI models fall into, and giving my interest into retrieval augmented generation and so on and so forth. I have seen that these strategies, these frameworks are not really ready for the prime time in sensitive applications. So this actually puts me into a burning questions in my head, and I want to just throw it out and keep the and in front of the community and see what interest arises in the space. So the first thing that the first question that I think of is, can we detect and localize these knowledge gaps? Right? LLMs have knowledge gaps. When I say knowledge gaps, I will talk about. I'll show you a hierarchy, and I'll also give you a more dense hierarchy of what these knowledge gaps are as down the talk. But I really don't know what about their representation, how that representation is connected to the ground truth or the knowledge structures. Do they access their knowledge when they are needed, or they just try to cook up something to give you an information? So we really need to detect and localize these knowledge gaps. The second is, can I take these internal model computations, which I call the computation graph, very famous term, came out from the TensorFlow literature, into more symbolic abstractions, where we can understand and localize these graphs into specific circuits, right? And in this process, when I'm localizing these gaps and understanding these neural circuits, can I understand them through the knowledge graph per se? And after that, we have done all of these things. The question is that now I understood. Let's take an example. Like I'm hypothesizing right now that let's say we understood which area or which segment of my neural network or by LLM is really the culprit for the problem. Can I do some targeted modifications over there rather than structuring the entire network altogether? And we are not thinking of doing it randomly. We are not thinking of doing it through data. We are really thinking of doing it through structured knowledge to see how can I resolve those gaps and make the model more adaptive to the domain that we are really wanted to work on. Okay. Yeah. So this is my thought of understanding of what these knowledge gaps are and what are the confounders in the LLM. So I want to just make this thing very clear in the separation of where we are in the LLM space. So when I say knowledge gaps, right, one of the things that really pops my head is the representation failures, right? Concepts are absent, right? Or the concepts that are present in the LLMs are not really the ones that we think of are useful for answering the question. But we get to know them only from the performance. We don't know them whether they are being in the vocabulary or when are they being used and things of the nature. Access failure means the model encodes, let's say, some information, but they are not really contextualized in the query that is being given to the model. The last part is more of most of an expression failure. Like even after I did the fine tuning and heavy lifting, and somehow I get to the point where the expression the model is making is retrieved, right? The application of those concepts are again a question of doubt. And that's where you put it into a supervised fine tuning. And again, you become more data driven as opposed to be more knowledge driven per se. Now, these are the gaps, but these are the gaps because of confounders that we see in the LLMs. The first one is the memorization part, right? The second one is what I call as a polysemantic interference, because you want, let's say you think of, let's say I want to have a smaller models for applications, but then every single neuron will now become more polysemantic, right? And you don't know what that polysemantic going to be. And there are some artifacts in which that are there in the data sets that actually are the constituent factors for increasing the memorization and polysemantic interference, right? And then at the end of the day, what we have is a model that do some shortcut reasoning, right? So this shortcut reasoning is what I call as a local source contribution, right? So let's just talk about this, what LSC means in the LLM space. So what does LSE is? So LSE is a behavior that I understood from the LLMs, the internals, which is which part of the input or the retrieved knowledge actually influence, right? I'm being very modest with the LLMs right this moment, but it's not really a retrieved knowledge, it's really a retrieved concept that actually influence the model's final answer, right? So high LSC means all the relevant tokens have been identified, correct reasonings are happening. High LSC also means that there is also misleading or local phrases have been identified, which can also be caused to high hallucinations and myth propagations. So both of these are like LSC is something that also can give you a right answer. LSC also can also give you a wrong answer as well. So this is a common trend in which how the LLMs trying to understand this behavior, right? So we found that this scenario is very much correlative to the attention that we really talk about. And we see that even if the model knows the answer lies in a multiple choice question answering setup, for instance, right, where the answer is there in one of those points, still the model makes a guess on those questions, right? And if you see over here, the LSE contribution score for the for a model, and all of these results are on the Llama and the Gemma, both of them failed in the scenario. We see that these models have been in a tendency where they really focus on what is happening in the nearby neurons and not really capturing the broader picture of what the question is, right? So that's where I see a lot of the confusion arising inside the model, and you can very much localize them. You can detect, so once you detect them, you can always localize them in certain layers inside the LLMs as well. So the idea was that to make sure that these LSC is being driven by knowledge as opposed to be driven by the data, which is the current mode of operations in various LLMs going forward, right? So this LSC also allows you to make sure that your LLMs are aligned to the domain specific resources. So this is a broader concept that is, think of this as a way that LSC is both a good thing as well as a bad thing. But if you really want to make it a good thing, the only way you can do it is by adding some sort of a knowledge into certain layers of the LLMs, right? So this can really gives you the behavioral interpretability, but I cannot really help in sort of elevating the gaps inside the model. LSE does not give that capability to me. I cannot elevate the problems. I can only interpret the behavior of the LLM, locate the things. That's all I can do with the local source contribution design. Right, and we saw that in truthful QA and in the HelioEval scenarios, which are the prominent data sets to really see the truthfulness structure of these LLMs. And we see that when we see their papers where, on the truthful QA study that happened a couple of years back, we see that the models have like 80% performance or truthfulness. But the moment we ask the model through LSC to pay attention to some of the, let's say, entities, numbers, and exceptions, and so on and so forth, like different symbolic triggers that we really care the model to pay attention to, we see that these models tends to have a higher hallucination rate, right? So now this creates a very nice, in my opinion, discrepancy between what is being tested in the truthfulness or truthful QA versus what the models are actually learned. Right. So when we look at these modifiers, named entities, numbers, negations, and exceptions, we see that these properties are never caught in making the decisions. Right. So hallucination on these are immensely high, despite the overall performance of the model on the truthful QA is there. So there is some sort of shortcut reasoning happening in the model that is diagnosable through symbolic structures, but now we really need to look at how do we correct them. We have a way of looking at identifying the segments in the model where things are going off, and we know that the hallucination is still high. Now we really need to look at how we can correct them. And we have seen this behavior in logical reasoning problems. We have seen it in the therapy problems where we have tested these LLMs that were released to truthful QA. And the one of the interesting factor that I really want to pay attention to over here is that on the right side of the table, right? The right side of the table, which is of the cognitive behavioral therapy. One of the clinicians actually told me that the model is heavily biased towards validation and reflection. It's not really doing questioning. It's not really doing this restructuring and so on and so forth. So this tells me that the way we are doing the fine tuning is just letting the model adapt to one soft space, comfortable space, which we in machine learning we used to call it as a VC, Vanosky, VC dimensions, where the model is comfortable in making the predictions. But it really didn't tell us that how we can move the model to have equal weightage for other segments in the problem space. So these are some of the problems strategy that we found that, okay, we have localized the regions in the model that are really the culprit for these behaviors. Now we really want to see how we can steer them or change their behavior over the time, right? So I want to skip this part because some of the things have already discussed in the part. So this is a bigger picture of the confounders and the knowledge gaps that I just laid down a couple of slides back, where I'm not talking about now a knowledge gaps, which is entity resolution, procedural knowledge, domain explanations. These are some of the gaps that I see in the LLMs. Negation, context, semantic relationships, directions. For each of these things, think of this that we can't have data sets being constructed for each of these gaps and confounders, right? To be a huge arena for data-driven AI as opposed to knowledge-driven AI, which we really want to go for neurosymbolic style. And most of this information are very much solvable through the neurosymbolic integration inside the generative AI structure. Okay, so what perspective that I bring in from symbolic is that this allows us to have structured knowledge being a core piece to be driving the LLMs. That's the first point, is that I really want to look at more about constraint aware generation in these models, which can be driven by knowledge graphs. The interpretability angle of these LLMs can also get benefited from the knowledge graph. And what you really end up doing is that you're sort of resolving the knowledge gaps inside the LLM without adding data. That's the prime goal of going with the neurosymbolic structures. So going further, when I say quantifying the knowledge gaps, I really want to talk about in the interest of time, I'll only cover one part, which is called the knowledge constraint probing for gap detection. And the second one is more about looking at making the RAG or the retrievers in more grounded through knowledge graph integration. So the first thing that I wanted to present in the session today is about the KG constraint probing, which is one of the way which we found to be very interesting in at least understanding that the model's concepts and features are the ones that align or that are present in the knowledge graph. So what we did was we freeze the LLMs and we read its internal signals first. We take a particular layer, we extract all the activations from that layer, and we want to understand what those concepts in those activations represent. Second is we have trained a sparse autoencoder over a knowledge graph, which allow us to give some representation of the concepts. We will see those concept representations that are there from the knowledge graph are mapped to the activations or to the concept and the feature space inside the LLMs. Third was to look at those information and see the discrepancies between the two. And from those discrepancies, we really want to update the LLMs or maybe like classify which are the weak entities, weak relationships or absent concepts and try to update the LLMs in that space. So this sort of gives a nice strategy for steering these models using knowledge graphs, leveraging autoencoders, the common mechanism of representation learning in neural networks, and also bringing a very nice flavor of neural space and the semantic space together in the probing mechanisms. We also examined that there is a very nice way of doing KG paths or knowledge graph path retrievals in the RAG that allows me to do two things. One is I can know which document was selected. I know why the document was selected and how the document was being used by the model in the decision-making process. So the step that we followed is the following. We start with an uncertain knowledge graph. We learn which edges of that knowledge graph are relevant based on the query and which of them are noisy. We rank the documents of how well those queries are being so we rank the document based on the queries and the path being followed. So think of this at the top. So I start with a user query, QE, and gradually go over the graph, identified which of the entities are noisy, and gradually over the period of time, I'm having a path of all the entities being traversed through this mechanism of optimizing the document retrieval and optimizing the knowledge graph as well. Right. And once you're done with this, it's pretty easy to have this traverse knowledge graph, to do a traversal over the knowledge graph using a breadth first search, retrieve the documents given based on the knowledge graph. And then lastly is to use that information, to use that retrieved documents for your answers. Now, here is a thing that I want to really emphasize. Your answers are not driven only by the document that you have retrieved. It also depends upon the enriched query that you got from the knowledge graph, as well as the KG path that you have identified from the graph as well. So this allows you to have a nice inference over the standard retrieval augmented generation mechanism. So this does not really give me an insight of the LLMs, but it really makes my retriever, at least my retriever, neurosymbolic compared to my generation. My generation is still the same, but my retriever is now becoming more neurosymbolic space with my KG integration. We tried it over like 6, 7, 8 data sets, and we consistently outperformed 33 billion parameter models with just 3 billion parameter model. On the KG path RAG and the Prono RAG that we had, both of them are just 3 billion parameters altogether, even with the RAG, and they did far better than, or relatively better than, 33 billion parameter models in per se. So this, I want to switch some directions over here and want to really, in the interest of time, just jump to the main angle of mechanistic interpretability in this space, where I'm talking about saying that we really want to have 3 key instruments for really understanding the internals of the LLMs. And now with the RAG in place, we have 2 LLMs in this picture. One is an LLM in the retriever, and other is an LLM in the generator side. So we really want to have first is a knowledge graph sparse autoencoder that allow us to modulate the internal representations of the model, at least study them. The second is more about interpretability of those representations and steering them, where much of the topics that what Lewis talked about are doing deductive, inductive, and abductive reasoning circuits are very much present inside the LLM, but they are not identified. They're not being used by LLM per se, right? And the last part is more about sparsification or sparsifying this entire network with the information that really matters to the So to really condense your model. Okay. So one thing that we really are proud of in terms of the neurosymbolic space was this sparsification of this gigantic big model that we started with, which is around coming up with some around 13,832 edges. Right now, we are working with it on only with the 7,000 edges of this network, but we are also sparsifying it further. So what we found was that when we keep on sparsifying this network with the knowledge graph, we are still faithful with like 91.5% with only 70% of the edges preserved. And we found this to be far better than LoRa and other mechanisms which are data driven compared to a knowledge graph driven sparsification of this model. So that means that if I have access to the internals of the model, I can chop some of the unnecessary circuits. I can identify more inductive, deductive, and abductive circuits and keep them and preserve them for my decision making rather than having it more data driven. Right. So this I want to summarize my conversation throughout that we talked about to 4 or 5 points that really drives the semantic mechanistic interpretability space, which is where the neurosymbolic angle, in my opinion, has a huge role to play. First is to have the detection of the knowledge gaps. Second is to localize the deductive, inductive, and abductive reasoning circuits. Very relevant to what Lewis just talked about in the previous talk. We can actually distinguish memorization from grounding the knowledge. We really don't want our models to memorize things. And then we can even targetedly steer these models without fully retraining them altogether. And at the end, once we have these models, we can now have an auditable way of explanations as opposed to make it more hunch-based scenarios. So I'm just putting thoughts of these three constituent ideas together, which is neural, symbolic, and the causal, put together into the semantic interpretability space for really having a deployable LLMs for real world applications. So this is where I want to stop and see if there are any questions. And going for my road ahead, some of the things I really wanted to add, and this I added after listening to what Lewis was mentioning. So we released this counter logic dataset that's through IJCNN conference, which allows us to test the internals of the LLMs on the logical reasoning part. We just completed a dataset on theory of computation of the finite state machines. Some of the things that we tried out with the clean closures and things. We released the ReDFA datasets, which is under review at TMLR. We looked at redefining the LLMs through rationals. We are also interested in looking at this memory-driven agents as well. And lastly, I already talked about the cognitive behavioral therapy per se, where we saw the bottleneck in the current LLM strategies. So all of this driven research are a part of my previous efforts. Started in 2024, where we talked about CREST, and these are all in sort of a nice causal research going into neurosymbolic AI space. With this, I thank you all for for giving me the time, and I look forward to any questions. And this is a very high level figure that I want to bring in, where I see a lot of papers talking about neurosymbolic. They're selling methods by the name neurosymbolic, but they're not really neurosymbolic per se. So this is just my small hierarchy about those methods as well. So chain of thoughts have been talked about as neurosymbolic, which I don't really think it's neurosymbolic. Tree of thoughts, self-consistency, DPO, RLAIF, instruction fine-tuning, they're not really neurosymbolic per se, because they're not really having a bidirectional neural symbolic integration altogether. So with this, I end my conversation and look forward to any questions there are from the audience. You're muted, Ram.
Your talk while you're talking. Again, thank you very much. Very exciting talk there, which went into considerable depth of various things, and we probably need a follow-up at some point on this.
Yeah.
But as Louis, I think it was a nice transition from what Louis has mentioned to you. But there are a number of questions here. I don't know what the time scale here, Ken, is now. We're supposed to go from 12 to 1.
Yeah, we're already over, but
Uh,
certainly these are very important talks. We could try looking at some of the questions.
because there are questions in terms of the level of integrations which Manas has pointed out, because you can have the integration of either ontologies or knowledge graphs at either at the input level or out level, are looking inside the neural network itself and fine tuning it. And this something was brought up. And I guess there are two people here. There are three people here who have been asking a lot of questions: Ravi, John, and Harshit. So maybe we can give each one about a minute or two, ask questions. John has his hand raised up right now. John,
Go ahead, John.
unmute. Yeah.
Okay, one thing that I want to emphasize is that for many applications, 99% accuracy is total failure. I mean, nobody would want to drive a car that will fail or have an accident on every 99 trips. No one would fly in an airplane that would have a crash on every 99 trips. For those things, you must have 100% accuracy or the option of doing something else to compensate. And in banking, for example, every transaction must be accurate to a fraction of a cent. You must have absolute precision in banking. And if you cannot do it, you must have a message that says you can't do it. And these are things that we have been doing with neurosymbolic, and we don't really, in fact, even putting neuro first is inaccurate because neuro is one important part of it, but it's not the whole thing. We have four kinds of reasoning: in abduction, deduction, induction, and evaluation, and all four must be absolutely precise.
Yes.
Fully agree. I fully agree. I worked in aerospace in industry, and you are 100% sure, correct. And sometimes we want 150% assurance. You're right.
Yeah.
Yep. And then we have Ravi.
Ravi,
He's
go
muted.
ahead, Ravi.
Ravi, unmute.
Can I be heard now?
Yeah.
Yes, you can be heard.
Sorry, I was muted. The question is connection between attention, which is part of cognition, and recognition by all these techniques that attention extent is measurable. Am I able to ask the question right way?
So Ravi, is your question that attention and other properties of the LLMs are measurable?
No, even if they are measurable, are they recognized by the models these days? Because this is a dynamic.
Okay. True. They are recognizable, but the score or the amount in which they are being recognizable are extremely small. Right. So somewhere down the line, what I see is, and this is coming straight away from my exploration in the local source contribution work, is somewhere down the line in the later layers of the LLMs, sudden shift in the concept happens. Now, why does it happen? I'm not really sure at this moment. But I see that the concept that it has lost in the middle, it doesn't recover that. So the answer over there is sort of correct, but it's not completely correct.
So
Okay,
I was
thank you very much.
thinking of comparison between process of thinking and process of these modelings that you experts have described. And I see that just as mind disconnects with the thought, similar things might be happening in machine.
Yeah, Ravi, it's a
Absolutely.
philosophical question, which again, I think needs some further discussion later on. So I'm just looking at the time right now, and maybe who else is Harshit? You asked any
Harshit?
questions?
Harshit.
Yeah. I have just a one small question. So currently, actually, the information are actually distributed across the weight, right? And we are trying to build a symbolic layer on top of it. So I was wondering, because right now there is no specific universal schema defined to compress any kind of surface level information into a basic, a smallest unit of information. And you can say, and when we take a cluster of that unit, we can say that, okay, this can represent that surface level information. So if we do not have a defined protocol, you can say a frame, what we are calling, like we are doing a research on that, that we are taking a surface level information and trying to compress that into a very small finite frame. We have we define what that frame is. So we are wondering that if compared to the adjusting a weight, uh, is that scalable related to representing a information in a small bits? Like you can define anything, like taking a inspiration from an ontology, like we can define any ontology layer and use the LLM to compress that information into that ontology layer, and then actually use that ontology to actually see which frames are getting activated when LLMs are actually answering the questions. So this is what we're doing.
It's a long question, but let's.
Oh, I don't know if I got the full question, but let me give you an example. One of my students, he did a very interesting work on, let's say, he uses the language model to read the text, to extract the relations, right? And on top of that, right, the LLMs, it handles the extraction, reading the text, and providing some suggestions for the symbolic system, right, from the text. He did this work for the agriculture domain. It was a very interesting work. However, the LLM system, of course, couldn't enforce rules connected with pathogens and with fungi and other diseases that you show in plants. So actually, the combination that we had with using OWL reasoners, using palette and other ways of handling the formal consistency was what actually worked in this case. So the external ontology in the domain as well, in agriculture, there's some very specific ontologies. One of them is called AgroVoc. They provide a semantic anchoring, as we called, that transform the vague labels into a formal URI with the knowledge relationships that have been extracted. So the LLM by itself would never generate the formal reasoning for the agriculture domain without the external source provided by the symbolic engine that we built. So this is perhaps related to what you mean.
Okay, so continuing on, I think Gary, you have a question. I think this is going to be your last question before we wind down here.
Yes, I had a question for Manus. You talked about the idea of steering the LLMs without restructuring it, without retraining it. You also talked about as restructuring it, making it sparse and things of that nature. We had a speaker 2 weeks ago, Randy Goebel, who talked about debugging foundational models. And I'm wondering if you're familiar with that work, or if you would agree that that's sort of what you're trying to do here, debugging the foundational model.
Yes. So so Gary, to that, I'm more driven by debugging it with some knowledge structures, as opposed to making another data, or like making it more data set driven. For instance, let me give you an example. There is this work called representation engineering called RepE, which sort of tells you that, oh, okay, I know that the model I have a data set which I want to test, and that data set is on truthful QA, let's say, to measure the truthfulness. And I know that model is making some mistake. So I'm not giving it more samples of truthful QA, but I'm giving it more samples of another data set that I know the model will look at it and compare and make it, and move in a correct direction. So what they try to do is that they add another parallel data set, which is contrasting to the existing one, so that the model measures the difference between the two, and then it gets steered in that space. So they say that in order to steer it, if you just give parallel data sets or parallel examples, that also can make the model steer in the direction of the correct answer. So this is what they referred as a representation engineering mechanism because there's no science behind it. We are not really investigating what the concepts are, what they represent. We are just giving it more negative samples so that it knows to value what are the positive samples that it's going to be looking at.
Okay. Thank you, Manas. And from with that, I think we'll close the session. Except Ken, you might want to give a little bit prelude to the section next week's session.
Yes,
Okay. Thank you, everyone.
thanks to our
Thank you very much
speakers and to our co-hosts for a very successful session with some very important work by both Lewis and Manas. Thank you so much. So with that, we are formally ending the ontologies and AI track, although we're going to have a synthesis session coming up at the end of April, where we can revisit these topics and continue the discussion. And of course, you can continue the discussion on the Ontolog forum. So next week, we begin the foundations and tools track of the summit, where I will be introducing the foundations and tools track and sharing it. And I'll also have a little talk about the notion of foundations and some history about foundations, especially in mathematics. And then we'll have a speaker, Professor Mandali, who will be speaking on faceted classification as a semantic framework. And then later in the track, we're going to have a number of other speakers. And I encourage everyone to come next week and also for the rest of the summit. And with that,
on that, Ken, actually, quick comment on that is the faceted classification is what I mentioned in my talk on ancient Indian ontologies. There was a paper by Ranganathan et al., and Devika is going to explore more on that. So that was one of the requests that we had to talk more about it. So Devika has kindly agreed to do so. And I mean, it's a kind of philosophical difference in a way between Eastern and Western. In fact, Louis Lamb had something called cogito ergo sum on one of his slides. Actually, in the Indian philosophy, it's more like sum ergo cogito. So it's the other way around. Instead of whatever it is, I think, therefore I am, therefore I think. So the emphasis will be on me, which with the thinking process comes out of it. Anyway, that's by the side. I couldn't help that, Louis, you had it on here. Pardon?
So yeah, it sounds like we're going to have a very interesting session next week. I encourage you all to come. And with that, we will adjourn today's session. Thanks again to the speakers, to the co-hosts, to all of our participants.
Have a good week, all.
Bye.